Hello, welcome to all of you in the tutorial session of applications of power electronics in power systems. This is the seventh tutorial session. I shall share my screen. Yeah. In last week, we studied about different types of static bar compensator. What were the different types? Uh, the different types of SVCs were first there was FCTCR, that stands for fixed capacitor thyristor controlled reactor, right? So that means that the capacitive part is fixed, but the reactive part, the reactor, that we can control by controlling the thyristors. And how we can control that? We can actually dictate when we can turn on the thyristors by deciding where the firing angle. Based on the firing angle, the 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 instant at which the thyristors are turns on, that changes. And by switching at but by varying this firing angle, we can have different susceptance, right? We can vary the susceptance, the effective susceptance, and that's how we can have different variable compensation. So that was the first type, FCTCR. And then there was TSC-TCR, thyristor switched capacitor, and then thyristor controlled reactor. So for capacitor, we don't vary the firing angle. Thyristor switched capacitor means either the thyristors will be fully on or they will be fully off. Uh, that is the capacitive part, and the reactive part is again same, thyristor controlled reactor. Now we also discussed about some of the challenges we face while doing switched capacitor compensation. Why? Because for switched capacitor compensation, transients are generated, right? There are some transients, and we need to mitigate them. And we also discussed some of the methods by which we can mitigate those transients. Okay. These were the things that were discussed in the last class. In today's tutorial session, uh, we shall talk about the role of SVC in transmission line. Now, one of the most important roles that of the SVC is obviously for the reactive power compensation. That's what we have been studying in the last few weeks. And why reactive power compensation is required? It is required because uh, they during light load condition there may be severe over voltage, and during rated load or near about rated load, there we may face severe under voltage, right? So that, and that is detrimental for the power system and the equipments. So, to control that, to maintain the voltage at a safe value, we need reactive power compensation. And that's when the role of SVC comes, static power compensator. That is the main role, to maintain the voltage, right? That is the first part. But other than that, SVC, they are beneficial for some other purposes also. What are those things? Firstly, it can improve the steady state power transfer limit, right? It can improve the steady state power transfer limit. How it can improve that we will see. Next, it can improve transient stability margin. Okay. So this has already been discussed in the class, and we shall also talk about it in this tutorial session. And it can also provide damping. So whenever there are transients, there will be some overshoots and undershoots. And what is damping? Like damping means we can damp them out. We can reduce those overshoots and undershoot magnitudes by damping the oscillation, right? So the SVC can also provide damping. So the applications I just talked about, those have been listed here. So firstly, the steady state power transfer capability, it can increase. That is the first point. Then it can increase the transient stability of the power system. Then it can provide damping. And lastly, it is used in voltage control. That is already known. So the first point was that SVC can increase the power transfer capability, steady state power transfer capability. So let's see. For that, we may take a short line, a short lossless line, whose reactance is X, and this is in lumped form. This is the source, the sending in voltage. This is V1 angle delta, and this side the voltage is V2 angle 0. This we can take as an infinite bus. This we can take as an infinite bus, and the voltage we can take V2 angle 0. And if these are the voltages, then what is the steady state power? The steady state power is V1 V2 by X sine delta, where delta is the power angle, right? Delta is the power angle. And then what is the maximum value? Obviously, the maximum power will be when delta is equal to 90 degree. In that case, P is equal to V1 V2 by X. That is the maximum power. So P max is equal to V1 V2 by X. This is the maximum power without any compensation. There is no compensator attached to the line. Okay. In that case, this is the maximum power. Now, suppose in the midpoint here, an ideal SVC is connected. This is the static var compensator connected in the midpoint. And these are the reactances x by 2 from sending end till the midpoint, and then again x by 2 from midpoint to the receiving end. In two equal halves we can divide, because this is a symmetrical lossless line, short line. So and the reactance is in lumped form. We can divide this into equal halves. Okay. In that case, what is the transferred power in steady state? So PC, the power during when there is compensation, that is V1 Vm by X by 2. Why? Because now the reactance is X by 2. So the 2 comes in the numerator. It becomes 2V1 Vm by X sine delta by 2. Why? Because the angle from here to here, the power angle will be delta by 2. Because we are considering the midpoint here. Okay. That's why it is delta by 2. Again, what will be the maximum power? Maximum power will be 2 V1 Vm by X. And if this is a symmetrical line, then we can we can say V1 equal to V2 equal to V. we can take. Okay. And if the midpoint voltage is being maintained at this value, then we get this expression 2v1 v2 or 2v square by x. Okay. If you see this value is twice the previous value, right? So when there is compensation, midpoint compensation, then we can increase the steady state power two times the power when there is no compensation. That's why it is told that SVC can increase the steady state power transfer capability, right? So this is obviously an advantage because by providing this compensation, we can transfer a steady state power which is double the power of the case of the uncompensated line. Okay, this is double the power of uncompensated line. Now this was the active power. What about the reactive power? The reactive power is this. Okay. Now if you simplify this, it becomes 4v1 square by x. You just assume a symmetrical line. So throughout the discussion, just assume this as a symmetrical power transfer line. So v1 is equal to v2. The magnitudes are equal. So this is 4v1 square by x 1 minus cos delta by 2. And at if delta by 2 equal to 90 degree, then this is 0. The maximum value is 4v1 square by x. So this should be the the power limit, reactive power limit or the power rating of the SVC if we want to if we want to increase the steady state power to twice the previous value. Okay. But practically, if we speak of it, this is not possible. 4v square by x, this is too large a value, and we can't install such a SVC in the power line. Okay, this is not practically feasible. So we can still increase the power transfer limit, but not twice, but slightly lesser than that. Okay, because if because this 4v square by x rating, this is too large. Okay. So but these are the theoretical limits. Theoretically it is possible, okay, to transfer a power of this amount. These are some of the curves. Over here in the left hand side we have P versus delta. Now this purple one, this is the curve for the uncompensated line. Then we have we have this one when there is compensation. So that's why you will see the maximum value here is 2p max, whereas here the maximum power is p max. And the red one, this one is the QSVC. Its rating is 4p max, 4 times the power of uncompensated line. Okay. So that's what we discussed in the last slide. And here we have the some other some other curves. So again we have this curve for the uncompensated line. Then this red one here, this is this is even lower than the uncompensated line. So when do we get this curve? When the SVC is operating as fixed inductor. We already know what is fixed inductor mode and what is fixed capacitor mode. So we already solved numericals and studied when do we operate the SVC in fixed inductor mode and when do we operate it as fixed capacitor mode, right? So in fixed inductor mode, the maximum power again reduces further, and this green one here, this one, this is the curve for fixed capacitor mode, right? So what is the operating region for us? The operating region will be, it will start from here, it will follow this blue curve, this one, till this point. Till this point it will follow. Then from here it will follow the fixed capacitor curve. Okay. From here it will follow the fixed capacitor curve. But till this point it will follow the blue curve, this one. Okay. So you see, we can still get a power which is higher than P max, right? So which is higher than this point, but it is not exactly twice, right? It is not exactly twice, but higher than P max. Okay. So now we can start the problems. The first question is, what is the main function of SVC in a power system? So that we already discussed. So used in voltage control of power system, SVC is used in frequency control of power system to control the current in transmission line, and lastly it is used to control the loading of transmission line. So obviously here the first option is correct. We use SVC to control the voltage. Next question. What is the theoretical steady-state limit of power transfer for a midpoint compensated transmission line where the midpoint voltage is held at system voltage? So they are specifying that midpoint voltage is held at system voltage. So if you are considering a symmetrical line, then V1 is equal to V2 is equal to V. Okay. But this is only the magnitude, okay, not the phase. This is in terms of magnitude. So their magnitudes are same. And you are also maintaining the midpoint voltage at V. So Vm is also equal to V. And how you are doing it? You are doing it by the SVC, by installing a SVC. So in that case, what is the steady state power transfer limit? That we just discussed, that we get twice the theoretical steady state limit of an uncompensated line. If there is no compensation, then if the maximum power is P max, and when there is compensation, we get 2 P max. So option B is the correct option. Then third question. What is the rating requirement of the SVC to hold the midpoint voltage constant at system voltage for a short lossless transmission line? What is the rating requirement? That also we have discussed. The rating should be 4V square by X. This is theoretically. This is the theoretical rating. 4 times the maximum power of an uncompensated line. Okay. So you just remember these curves. This one for uncompensated line, then this blue one, this is the ideal case. Okay. So you get 2 P max, this is the steady state power, and then this is QSVC, this is the rating of the SVC. Okay, ideal rating. Okay. What is the synchronous power coefficient for an uncompensated line, where sending end voltage is V1 angle delta, receiving end voltage is V2 angle 0, and X is the reactance of transmission line. Now, what is synchronous power coefficient? Synchronous power coefficient is this quantity, del P by del delta. Del P by del delta, okay. This is the synchronous power coefficient. Now we already know the expression for P. What is the expression of P? It is V1, V2, V1, V2 by X sine delta, right? This is the expression. So for finding out synchronous power coefficient, you will have to differentiate it with respect to delta. This becomes cos delta. Hence, the synchronous power coefficient is V1, V2 cos delta by X, option B. Okay. The fifth question, which of the following statement is true about the power flow in a short lossless transmission line with midpoint SVC? The first option says the power flow in the line when SVC is providing capacitive compensation is greater than the power flow of uncompensated line. The second option says the power flow in the line when SVC is providing capacitive compensation is lower than the power flow of uncompensated line. The third option says the power flow in the line when SVC is providing inductive compensation is greater than the power flow of uncompensated line. And the last option is the power flow in the line when SVC is providing inductive compensation is lower than the power flow of uncompensated line. Okay. So the power flow in the line increases when there is capacitive compensation compared to the power flow of uncompensated line. Okay. So the first option is correct. And here the power flow in the line when the SVC is providing inductive compensation is lower than the power flow of uncompensated line. This is also true. This is also true. So A and D, these two options are true. Okay. The next question. Which of the following statements is true? The marginal area of P delta characteristic of SVC compensated line is lower than uncompensated line. Now what is the marginal area? That we need to know first. What is the marginal area? Now in basic power system course, you must have studied about the P delta curve and the equal area criteria. Now, if this is the P delta curve, then the curve looks like this. So it gradually rises from 0, then it reaches peak, reaches its peak, and then again it comes back to zero here. And suppose this is the operating point where P mechanical is equal to P electrical. Where is the mechanical power? The mechanical power is the power that is provided to the generator, right? Because you need to rotate the generator, and then at the output of the generator you get the electrical power. So suppose this was the operating point, but suddenly there was this load change. Then there will be some accelerating area and decelerating area that will get generated, right? So now you come here because your electrical power suddenly becomes zero, but the mechanical power can't be zero immediately because mechanical quantities they are much slower than electrical quantities. So you get this area, this is the accelerating area, this red striped one, and then again you get back here, and then this green one, this is the decelerating area. So for the stability of the power system, the accelerating area should be equal to decelerating area, right? And this area, this blue one over here, this area is the marginal area. Okay, this is called the marginal area. This is the marginal area. Fine. So the marginal area of P delta characteristic of SVC compensated line is lower than the uncompensated line, and marginal area of P delta characteristic of SVC compensated line is higher than uncompensated line. Marginal area of P delta characteristic of SVC compensated line is equal to the uncompensated line, and the marginal area of P delta characteristic of SVC compensated line is negligible. So again, we will compare the marginal area of the uncompensated line and the marginal area of a compensated line. This left hand side diagram shows the P delta curve for the uncompensated line, and the right hand side diagram, this is the one for the compensated line. So here if you see, so this if you follow this line, this yellow line, you can see that this marginal area here, this is much higher than the marginal area of the uncompensated line, right? So here this decelerating area slightly decreases. Okay. So this area slightly decreases, but here the marginal area is much higher. Okay, much higher than the uncompensated line. This is another advantage because it provides higher marginal area. That's why the transient stability gets better. Okay, for a compensated line. This is one of the advantages of the compensated line. Okay, so the option B is correct here. The marginal area of P delta characteristic of SVC compensated line is higher than uncompensated line. Okay. The next question. If the synchronizing power coefficient of an uncompensated lossless line is positive, then the system is. So in a previous question, we discussed that synchronous power coefficient is del P by del delta. This is the synchronous power coefficient. Okay. So when the synchronous power coefficient of an uncompensated line is positive, what does it signify? That we will see. So here, if you see, this equation is called swing equation. If you have studied basic power systems, you must know that this is called the swing equation, where m is the inertia constant and d square delta by dt square equal to p mechanical minus p. Okay. Now, if there is small perturbation in the system, then we can we can write the swing equation like this. So this delta is del delta. Okay, and this is del P mechanical and del P electrical. Okay. Now just del P mechanical is very small because the mechanical quantities they change in a slower pace than the electrical quantities. So that's why it is almost zero. So the equation becomes this, and then you can write it like this. Okay, you can write it like this. So this del P by del delta, this is the synchronous power coefficient. Okay, this is the synchronous power coefficient. And then you can convert it like a standard differential second order differential equation, and you can solve it. So if you solve, if you so this is the okay. So if you just solve it, what you will get? So this is the linearized swing equation. Then you will get two equations, right? Sorry, you will get two solutions. If they are lambda 1 and lambda 2, then these are the solutions, right? Now here comes the part. So if Ks is the synchronous power coefficient. If Ks is positive, in that case, you get these solutions. Both of them are imaginary. Plus minus j root Ks by m. So they are imaginary. And when you get imaginary solutions, then your system is marginally stable, right? Because the solutions are on the imaginary axis. So you get the solutions which are on the imaginary axis, and the system is marginally stable. And if Ks is negative, then your roots are real, and then the system is not stable. The system is unstable. Okay. Now we will go back to the question. What was the question? If the synchronous power coefficient, that is Ks, if Ks is positive, then the system is marginally stable, right? The system is marginally stable. Okay. Which of the following limits of power transfer is lowest? So there are some limits. There is steady state stability limit, then there is thermal limit, then there is transient stability limit, and then there is electrical damping limit. Okay. So the lowest limit is electrical damping limit. Okay. This is the lowest limit. Okay. The next question. Which of the following is true about the role of SVC in damping? Now, one of the advantages of SVC is it can provide damping. So, from the swing equation, you can understand that there are some oscillations in the power system, right? So, the the so the whenever there are transients, there are oscillations, there will be some overshoots and undershoots. There are some overshoots and some undershoots. So the quicker we can damp them out, the better is for the system, right? The then and this damping, the SVC can provide the damping to the oscillations. Okay, it can damp out the oscillations. So what are the options? By keeping the SVC voltage constant, the power angle oscillation can be reduced. SVC with momentary voltage modulation can damp the oscillation of the power angle. SVC operating as fixed inductor can increase the voltage resulting in additional decelerating area. SVC operating as fixed capacitor can decrease the voltage, resulting in additional accelerating area. So the correct option is we can perform momentary voltage modulation, and that's how we can damp the oscillation. Option B is the correct option. So this is the way we can modulate the SVC voltage momentarily, and we can provide damping in this way. So you can see the detailed explanation in the lecture notes and in the video lecture also. Okay. Okay. So now I will take a 10-minute break, and then I will discuss the rest of the problems. Let's proceed to the next question. If a transmission line is divided in equal sections with an ideal SVC at each junction of the sections that maintains a constant voltage, which of the following is a correct expression of power transfer theoretically? So there is a power transfer line. At the sending end, there is a source. There is a source. And then there are n equal halves. Okay, like this. There are n equal halves. So like this, it just continues. And here we have the here this is the receiving end. V2 angle 0. Okay. And this is V1 angle delta. So if this is the case, then what is the expression of power transfer theoretically? So for when the transmission line is divided in two equal halves, in that case we already derived the power transfer, the expression of the uh, power transfer, right? So and obviously there is SVC connected, so the SVC is connected right here at the junction of the sections. Okay, so SVCs are connected at each junction like this. Okay, so at each junction, the SVCs are connected like this. So when the transmission line was divided in two equal halves, in that case, we already found out what was the power. The power PC, if you remember, the power of the compensated line was V1, V2, V1, V2 by X by 2, because the we can equally divide the reactance into halves, two equal halves, from the sending end to the midpoint and from the midpoint to the receiving end. And here it was sine delta by 2. Sine delta by 2, right? This was the expression. Now you can find out for n sections. So this became 2v1 v2 by x sine delta by 2. For n equal halves, the expression becomes, we can draw analogy from this one. Okay. So this becomes p square by x by n sine delta by n. Okay. So this is x by n and this is delta by n. Okay. So yeah, so that's what I showed here for the when there are two sections in that case, and for n equal halves, this will be the expression. Okay. So the next question. If an SVC operates in inductive mode, its effect on system voltage is. So the SVC is operating in inductive mode, right? Then what is the effect on the system voltage? So in the last tutorial session also, this we discussed. So when do we operate the SVC in inductive mode? When do we operate it in inductive mode? When there is an over voltage, right? And when there is an over voltage, when the load is light. in light load condition. During light load condition, during light load, right? We face the over voltage issue, and in that case, the SVC operates in inductive compensation mode, okay, during light load. So what will be the job of the inductive compensation? The job will be to absorb reactive power so that the voltage reduces, right? So obviously the system voltage decreases, okay. When SVC operates in inductive mode, the system voltage decreases. The next question, the marginal area of the P delta curve indicates. What does the marginal area of the P delta curve indicates? The marginal area indicates the available area to satisfy equal area criteria. Okay. Because there is accelerating area, there is decelerating area, and marginal area is the area available to satisfy the equal area criteria. We will again refer to this diagram. So if you see, this portion is the marginal area. Okay. So this area is here to satisfy the area available to satisfy equal area criteria. So this is the margin. This is basically the margin to satisfy this criteria. Okay. So next question. What is the benefit of installing SVC in transmission line? So increasing the steady state power transfer capability, increasing the transient stability margin, protection from severe under voltage and over voltage, and lastly, all of the above. So the correct option is all of the above because it does all the work. It increases the steady state power transfer capability, increases the transient stability margin, and then protects from severe under voltage and over voltage, right? By by absorbing reactive power or by injecting reactive power. So all of the above. This is the correct option. Next question. For a lossless transmission line of reactance X equal to 0.5 per unit, sending and receiving end voltages are equal to 1 per unit. Find the synchronizing power coefficient at delta equal to 30 degree. Okay. So this is just a very small numerical problem. We have already discussed this. So what are the parameters? So V1 equal to V2 equal to 1 per unit. This is the system voltage, 1 per unit. And the reactance X is 0.5 per unit. Okay, 0.5 per unit. Per unit. So what is the synchronous power coefficient? There is no, they have not mentioned anything about compensation. So we will consider the case of an uncompensated line. And what is the synchronous power coefficient for an uncompensated line? Del P by del delta. Del P by del delta is equal to V1 V2 by X cos delta. Cos delta. Okay. So just substitute the values 1 multiplied by 1, then 0.5 here, and cos 30 degree. The delta value is 30 degree. So this is cos 30 degree, cos 30 degree. Okay. So what is the synchronous power coefficient then? In multiplied by cos 30. Right? So 1.732. So cos 30 is root 3 by 2. 1.732. This is the synchronous power coefficient. Okay. Next question. A 400 kV 50 Hz short lossless transmission line has reactance X equal to 0.3 per unit. An ideal SVC is installed at the midpoint of the transmission line. Find the theoretical steady-state power transfer limits with and without compensation. Okay. Theoretical steady-state power transfer limit. So this is very easy. Without compensation, if we consider, so first is without compensation. We consider without compensation. So without compensation, what is the steady state power transfer limit? That is P square by X, right? For a symmetrical line. So we can take the system voltage 1 per unit. So this is 1 square by 0.3. Okay. 1 square by 0.3. So divided by 0.3. So this is 3.33 per unit. Okay. 3.33 per unit. This is without compensation. And then with compensation, it's very easy, just multiply it by 2. So PC max, this is P max, we should say, because this is the maximum power transfer. So PC max is 2 multiplied by 3.33, right? So this is 6.66. 6.66 per unit. Okay. So this is without compensation and this is with compensation. Okay. So these were two small numerical problems. Okay. So yeah, so I guess these were all the questions that I wanted to discuss. So if you have any doubt, you can you can mail me, okay, or you can ask me in the next tutorial session. Okay. So, yeah. Okay, thank you. Thank you for your attention. We shall meet in the next